So good afternoon, everyone. So this is a lecture that will be where we will discuss about Nitsche's lemma and inverse and trace inequality. And if we will have time, we will apply inverse and trace inequality to prove parts of the a posteriori error estimation results. And in particular, we will be discussing about reliability of a posteriori error estimation, of residual based a posteriori error estimation, which comes naturally and very simply once we have discussed a little bit about inverse and trace inequality. Okay, so a very short recap about what happened in the last lecture. So this is the outcome of the results that we did in the last lecture from the practical point of view. And this is the L2 error and the H1, the L2 error and the H1 error for Q1 finite element types. So Q1 finite element types, let me remind you, are Lagrangian type finite elements in which the degrees of freedom are defined on the vertices of reference triangle, which is this, and a reference quadrilateral, which is this reference square that you see here, and then mapped via Q1 mapping to general quadrilaterals. And the Q2 finite element space instead is tensor product of quadratic polynomials on the two axes that you see here. And as we observe a convergence rates in terms of the H1 error, which is 1 in the case of Q1 and 0.5 in the case of H1 error and 1 in the case of L2 error, when you plot this against degrees of freedom. And for the type of meshes that we're looking at here, the degrees of freedom is related to H, as degrees of freedom square is basically 1 over H. So I have a square number of degrees of freedom that corresponds to, so the square root of the number of degrees of freedom corresponds to H, which means if you look at these error rates and you express these error rates in terms of H, you would see 1 here and 2 here. And on the other side, you would see 1 for the H1 error and 3 for the L2 error. And now today, so what we have seen so far explains this plot that you have here. So it explains the top part of the plot. So we were able to prove in a rigorous manner the H1 error for the finite element methods, and we were not able to prove in a rigorous manner yet the L2 error for the finite element space, and this is what we're going to do today. So the instruments that we have used in order to do this were the Danelion lemma and Bramble-Hilbert lemma. So three things actually. So Danelion, we will recap this in a very short and compact way. Danelion lemma states that if you take the k+1 semi-norm on a domain T, this is equivalent to the infimum on polynomials of order k on T of the norm U plus Q, and this again UK+1 PT. And with this notation, what we're saying is that there exists two constants which are independent of anything that appears in the slides over here. And it's telling you that the semi-norm is equivalent to the quotient norm. And here, sorry, I forgot to add the k+1 norm here. So I have to move this back. So this over here is actually k+1 PT. And then we put this together with the two other results. The first result is the scaling argument. So the scaling argument was that if you take the semi-norm V as PT on Tm, and you transform it back and forth to the reference element through a affine transformation, and the affine transformation is the affine transformation that transforms T hat into Tm, then you can show that this is actually proportional to rho m to the minus s. So the minus matches what happens on the left, times hm to the power k, semi-norm u k p tm. So this is the second most fundamental results that you should keep in mind when you do this type of things. And the third result is the actual meat that is used to actually prove the error estimates, right? So the third result is the Bramble-Hilbert lemma. Bramble-Hilbert lemma, and this lemma we wrote as there's a tau, which is in the linear space between and here wk plus 1 of any domain omega into ws any domain omega, and then Bramble is and such that the polynomials of order k defined on omega is included in the kernel of tau. Then the consequence of this is simply that you can state tau of u in the norm S. Sorry, here I forgot to write the P, of course, WSP. This is not SP omega. We have that this is controlled by the operatorial norm of tau times the semi-norm u k plus 1 p omega. And this result comes from a simple application of a couple of well, the proof is a one-liner proof in which you simply state that tau of u plus p is equal to tau of u by the hypothesis, and then this means that you can take that p to be the infimum over OP to minimize the S norm, and then as soon as you have that, you can simply state the scaling argument on the right, and together with the scaling argument, you can use the Needlian lemma. So you have the k plus 1 norm on the right on u plus q, and you stated that is equivalent to writing the k plus 1 semi-norm on the u. So once you have these two things, what we have proven, what we had proved, was the following thing. So for any f, in V star, and in what we discussed so far, we said the V was the space H1, 0 of omega. Okay, and for any f in V star, the problem AU equal F in V star admits unique solution if A is coercive, assuming that A is a object that goes from V2 to V star, a linear function that goes from V to V star, we wrote the finite element versions of this guy as this was in VH star, where VH was included in V. And from these two, we got to the conclusions that the norm of U minus UH in V star, in V, so this was the V norm, is controlled by the norm of A divided by alpha, where A is coercive with constant alpha, which is written over there. And this was the infimum on VH in capital VH of the norm of the exact solution minus VH. And now we kept going with this inequality And what we found was that U minus UH semi-norm norm 1, there's two constants here. There's one, there's A star and alpha, and this infimum was certainly smaller than U minus its interpolation. And once we had this, we basically globalized the inequality that we provided at the beginning on the U minus the interpolation U over H. So this can actually be written as the norm of A star over alpha. And there was a HM. So this was we call this simply H to the power K plus 1. And this was U to the norm K plus 1. And sorry, the plus 1 here is not there. So this was U K plus 1 omega. And the reason why the UK plus 1 is not there is because the plus 1 that should appear here has to be compensated with the minus 1 that comes from the left-hand side of it. Okay. And the reason is because we are exploiting the estimate that I've just shown here. So I'm applying this to the interpolation operator. So the interpolation operator is an object that has, if you are in a finite dimensional space, which is derived by polynomial spaces of order k, then the interpolation with respect to the order k has its kernel in tau. So if you take I minus, in particular, U minus the projection of U onto so this is the projection onto pk, is an example. Okay, so in this particular case, if you take the projection of U, the local projection of U, actually the interpolation of all functions U on the finite dimensional space, if you restrict those interpolation to each one of the single elements that make up the domain, you would get over here the sum over all the interpolation on the size tau, and then we have defined here H as the maximum for M of HM, and we also have assumed that rho M was greater equal than sigma HM for every M, so that exists sigma greater than 0 such that rho M is greater or equal than sigma dot M, and we say that this is a quasi-uniform grid. And just to be precise, the distinction between quasi-uniform grid and shape-regular grid is simply the fact that in the quasi-uniform grid, this in the shape-regular grid, you have that HM over rho M is 1 over sigma M is bounded away from 0, but that doesn't say anything about the fact that this H is bounded away from, that these H's are basically the same over all the grids. So the idea is that if you have a quasi-uniform grid, then the grid is shape regular. So you have this property that is written here on the bottom, and you also have that you can control the H in a uniform way from above and from below, together with rho M in a uniform way from above and from below. Okay, so let me keep going in this direction. So once we have this, what we were trying to understand is why we observe the actual better convergence rates in the L2 norm. So the error convergence that we had in the interpolation error, well, the interpolation error justifies what we say in the sense that the interpolation error for BH is we have the operator that I brought there as IH. So we define IH that goes from V to VH. And if you recall this, we had defined this as a function that returned for every U, the dual basis extension of that applied to U times VI, where these were the global basis functions to define what the space capital VH is. So this VH is the span of VI for I that goes from 1 to n. And what we have here as well is that the Vj over Vi or applied to Vi is delta Ji, and we have the V tilde is Han-Banach extension of Vi on V star. Okay, so this is the definition of the interpolation that we have used so far. And of course, there's several ways in which one can do this, one can do possibly this extension over here. So I'm not discussing how one will produce this Banach extension in these particular cases. What we know, however, is that for functions that are regular enough, so k plus 1 of omega, then for k strictly greater or equal than 1, what we obtain is that hk plus 1 of omega is also a subset of C0 of omega, and this is equal for d equal 1, 2, and 3. Okay? In all three cases. If you want to look at this in terms of d equal 1, then k should be, it's actually sufficient that k is greater or equal than 0. So also for h1, it's a continuous function in 1D. In two dimension, this is no longer the case. So in two dimension, one has to be careful. And in fact, if you want to be continuous, you have to have h1 plus epsilon, with epsilon, which is a strictly greater than 0 constant. And for instead, in three dimensions, this epsilon has to be, so the functions which are included in C0 are actually h1/2 plus epsilon for any positive epsilon. So there is some of embedding theorems that tells you when this is actually the case. So for the cases in which you have the continuity, one thing that can be expressed in this particular case is that you can use as an extension of Vi prime on the dual of V star. You can define this interpolation operator in this particular space, which is a more regular space. And for Lagrangian finite elements, this means that V tilde I is actually coincident with Vi, in the sense that these actually are the direct delta distribution centered on the nodes of the triangulation. So you're actually allowed to take the interpolation. And in this particular case, what you know from the theory that we have proven so far is that if you take the interval, the IH interpolation of U, and you take the sum over K, sorry, the sum over M of this with the S on the left-hand side taken over, so I'm using HK as a space, so this is taken over TM. So if I take the sum over all these guys, what I know is that this is smaller or equal than H to the power K plus 1 minus S. And in particular, one can say, instead of K plus 1 minus S, one can write L minus S U L of omega. And this is for 0 smaller or equal than L. Sorry, smaller or equal than S, smaller equal than L, smaller equal than K plus 1. Okay, So in particular, this pointwise estimate becomes what we have used above in the particular case in which you have m equals 0 or m equal 1. And for m equal 1, you get the H1 estimate. And you can use the global estimate, so you can use the global norm on the left-hand side, provided that the finite dimensional space that you consider in VH is actually included in the space H1. So for every space in which this S, in which VH is included in S, this becomes, the left-hand side becomes the global norm. For all the other ones, it's just a broken norm. So it's broken norm, it means it's a piecewise norm which you define in each one of the elements. Okay, so now if you take a look at this result doesn't tell you anything what happens to the H2, to the L2 norm with respect to the exact error. So with respect to the error that you have in the finite element space. So in particular, what we know from U minus UH in the H1 norm, we know that this is H U 2 of omega, but we cannot say anything about the L2 norm on the left because we don't have here the interpolation estimate. So we have something, we have to do a little bit more work for this to be the case. So let me try to apply this into to try to figure out how to make this work for the L2 norm, and let's delve into the details of the L2 norm. So I'll try to do this in a more general framework with respect to just the H1 case and the L2 case. So bear with me for a few minutes. So let's assume that that the space V is a dense subspace of H and is continuously embedded in H. And we assume that we identify H star with its dual. Think about H1 space for V and L2 space for capital H. This is typical in these applications. And we make these two assumptions. So the first assumption that we make is, of course, that if you take the normal view H, this is controlled by the normal view V, and this is for any U in the space capital V. And second assumption is that V is then written as the closure of H with respect to the V norm. And we would like to understand what happens if we use a source term, something which is more regular with respect to just something which is in the dual of V. And the reason is, we know that the bilinear operator that we have defined previously for the finite element space, which is this bilinear, well, the bilinear operator induced by this capital A that we have here, has a regularization property, in the sense that whenever you have a function f, which is with a certain regularity, the solution u is going to be more regular with respect to the function f, because there's some differential operators involved in the definition of the operator a. In other words, if you know that if the function f is continuous, then u is going to be C2 for the strong formulation. So if you know that f is in L2, then you expect the solution u to be in H2 in several locations, especially if you have some regularity for the domain. Even if the regularity is not a boost of 2 orders of regularity, you might have a boost of lower order of regularity. However, you can exploit the fact that you know the exact regularity of the solution u, and you know how to treat the more regular terms on the right-hand side by exploiting this in terms of some error estimates you can have on the right. So let me show you this. Let me show you how to do this by when we select f in a space which is more regular with respect to the dual of V star, maybe included between V star and V, and then what one can do is identify the elements of the dual of that space with the space itself, as we are doing here, and apply a couple of tricks, which are usually to obtain higher order regularity estimate. So this is exactly what we are going to do. So for f, which is in H, we write F tilde, the Han-Banach extension of F to the star. And that simply means we define F tilde V to be that object such that if you take scalar product in H, so H is a Hilbert space, because it's a subspace of Hilbert space, and assume that this is what's written here. I didn't say that, but this is a Hilbert space. That's a Hilbert space. This is the scalar product induced by, well, this is a scalar product that induces the norm in capital H, which is defined over here. And what we have here is that we assume that this is valid for any function V, which is in capital V, and we're basically identifying F tilde with F using the scalar product in H. And one can do this simply because we have identified H with its dual. And if you think about the L2 product, this is very often what happens. And whenever you have that function is in L2, you can actually identify this function with the dual function, and simply by using the scalar product in L2 to define the action of this dual function for every dual function that is there. Okay. So we have defined it in this way. And of course, what we know is that if you look at the way this is defined, one of the main properties, one of the obvious properties that comes out is that if you take the duality between F tilde and V for any V, this is equal to writing the scalar product between F and V by definition. And now you can use Schwarz inequality. And by using Schwarz inequality, one has, this is smaller or equal than the norm of F in H. And of course, this is smaller or equal than the norm of V in H. And of course, all of the inequality that I have here should have a tilde there. And of course, now I can use the property of V to be a continuous subspace of capital H. And what happens here, it's what this is telling us is simply that the F tilde is injective. So this tells you that the Han-Banach extension basically is unique, and you can do this in a unique way. Okay, so let's go back to our definitions then. Given F in H, find U in V such that now we have the usual problem that we've always written in this way. And now on the right-hand side, instead of writing F tilde, as we would usually do, and we simply write the scalar product between F and V in the H2, and this is for any V in capital V. Okay, so we are solving the problem here. This is the so-called primal problem, AU equal F tilde. And now the interesting thing is that one can solve an associate problem with the functions with the actually a joint problem with the same thing. And let's take this observation. If one has that the primal problem has a unique solution, then one can conclude also that the dual problem has a unique solution. So how do we write the dual problem? The dual problem is usually written in the following way. So we usually write the dual problem by writing the test function. Instead of writing the test function on the right, as is written here, we write it on the left. And we assume that the unknown that we are looking for is find given G in H, find phi G such that this is satisfied. And this is usually written as the dual problem, AT of phi G equal G. The observations that I want to make here is that there exists for every G in H, there exists a unique solution phi G in V such that A transpose phi G equal G because of Lax-Milton lemma. One can apply this directly right away, and it comes out naturally from this. Okay. So what's the why am I introducing the dual problem here? Well, the problem is usually introduced because one wants to exploit the added regularity by the fact that G is an object of H instead of being an object of V dual, and one would like to conclude that an estimate of this type is satisfied. So the theorem that one uses, this is called Nitsche's lemma. One would like to measure the error not in the H1 norm, but in the L2 norm. So that means in the context, in the abstract concept that we are saying here, by showing that this can be controlled as long as you have control on the solution of the dual problem. So how do we do this? So the idea here is that you need to have U minus UH V, and this is still there, so the same thing as before. And then there's an additional term that appears in the theorem, and we will show that this is true in the very few lines. So it's actually quite simple to prove it. So we will do the proof right away, and then we'll try to understand what's written here. So we're taking the sup for G in H of the infimum for phi H in capital VH of what? Of the norm between phi G, solution of the dual problem, minus phi H, norm V, scaled with the solution of G in the H norm. So in a certain sense, what we would like to show is that we will show that this term here goes to 0 with a certain power of H according to the regularity of the problem that we're looking at and according to the regularity of capital A. So how do we prove this very simple lemma? And of course, as it is, this is not really very useful because you don't usually measure what's written here on the right hand side. But however, if you know, for example, that you can interpolate, you can use interpolation, and you can prove, for example, that phi G has certain regularity, then you can replace phi G minus phi H with phi G minus the interpolation of phi H, and then you can relate the regularity of phi G with the actual data that you have on the right-hand side of the problem that this phi G is solving, which is this guy over here. So this is exactly what we're going to do next. So let's start by proving this very simple lemma in this unusable form yet. And the proof is simple, very simple. So what we know is, we know that if you take A of U minus UH, and you test this against VH, this is equal to 0 for any VH in the space capital VH. And this is called Sea's lemma. And it's what helped us basically prove a lot of the theorems that we had before and a lot of the results that we had. Okay. First property. Second property. What we know about the dual problem is that you can take the dual problem, which is written as a V phi G equal to G V for any V in capital V. And you can exploit the fact that if you use as test function the error u minus UH. Sorry, there's a capital H there, which is mandatory. Otherwise, we cannot do this in an intelligent manner. Okay. So if used as a test function E equal u minus UH, since you're solving the dual problem, that test function gets actually multiplied by A. So it's A applied to that test functions times phi g to solve the dual problem. So what we obtain is that the dual problem satisfies the following identity. It's u minus UH phi g equal to G u minus UH non H. And this is for any V in capital V. And so far, this is valid also for any G in capital V, in capital H. So the idea here is that by solving the additional problem, the additional dual problem, one manages to put on the right, to put into perspective, the H scalar product between U minus UH and any function G. And then the idea here is that you can rewrite, since we identify H with its dual, we can also define the norm of WH as the supremum. Let me use the same letter that I have there, GW scalar product H over all G in capital H divided by the norm G. By definition, simply because the dual norm, the dual space is identified with the space itself, and you can identify the two norms in this way. Okay. And of course, this is due to the fact that there's always a rates identification between the two spaces, which are given for granted by, you're implying whenever you take this scalar product with H. Okay. So if you have this, now what you can say here is, if you look at the definition that we have over here, on the right, the only thing that is missing is taking the supremum over GH of these guys over there. And of course, we can also observe that independently on the phi H that you add on the right here, so you can add any arbitrary VH here on the right. So let me call this on the right. So what we have so far is that G comma U minus UH capital H, this is on the left, it's equal to, now we know that this is A of U minus UH, and this is phi G. And of course here I can add any arbitrary function, so subtract any arbitrary function, which is in the space VH, thanks to the orthogonality of the error. So this guy is over here times that guy over here, that gives you 0. Okay, so I'm just adding and subtracting something which is 0. And now, if I have it in this way, then what you can actually say, you can keep going on the right, and you can take the supremum over G on the left, and what you would observe is that if you take the supremum of G comma U minus UH H over norm of GH, this is exactly defined as, this is exactly defined as the norm of U minus UH H, and by the equality that we have there, this is exactly equal to the supremum of G in capital H of A of U minus UH phi G minus pH over the norm of GH. And of course, now this is valid for every pH, arbitrary pH. This is for every pH. So let me just move this back. For every pH in the space VH, and for this we conclude exactly that U minus UH is controlled by the norm of A star, the norm of U minus UH V, and then the infimum we have the sup for G in capital H of the inf for V for VH in capital VH of Vg minus VH norm V divided by norm G H. And this is exactly what we said above here. So this is the end of this proof. Okay, simply by applying the definition of the H norm. So we apply the definition of the H norm and we exploit the orthogonality of the error for the solution of the dual problem. So in the solution of the dual problem, what has happened here is that any arbitrary G will give rise to a unique solution phi G. Well, the suffix here depends on the fact that I'm taking G to be arbitrary, and this is the solution associated with that G. And I can subtract, if I use a test function U minus UH, and this is essential, so you have to be able to use U minus UH as a test function for your problem. On the right-hand side, what you get is you can add and subtract an arbitrary pH. You can add an arbitrary pH, you still get the same thing. And so that tells you that your now you can just estimate this bilinear form by exploiting the constant of linearity, which is this guy over here, these terms here in its relative space, and these terms in the B space. And of course, if you take the supremum of that with respect to GH, then you obtain exactly the terms that you've seen before. Okay? Questions so far? Okay. Now let's frame this into a context in which we assume the following thing. So we assume that K is the Sobolev degree of V, and that means that if you take the V norm, this is equivalent to saying the K norm on the domain omega. Okay? And then let's assume that instead S is Sobolev degree of H, and in particular, if you do it this way, this is supposed to be smaller or equal than K. And so what we're assuming is that the H norm, it's proportional to the S norm in the space from here. Okay. And we also assume that, so assumption 1, assumption 2, and assumption 3. In the assumption 3, we assume that H is R regular for let me write this L in S, comma S max. What does that mean? That means That is actually what we want to have is that a transpose is R regular for L in SM. So the adjoint problem is R regular. So the adjoint problem is R regular. That is that for every function G, which is in HL, with L, which is included between little s and capital M, there exists a unique solution phi G to A transpose phi G equal G, and that the semi-norm of phi G, when measured in S plus R, is comparable, is measurable with respect to the norm of G in the from the way that I wrote this. This is L plus R, and this is L for all S for all L which is smaller, greater, equal than S, greater, equal than SM. Okay. So if I'm looking at this at this property, so this property is telling you, look, if you have a solution which is so Laplacian on smooth domains, for example, is 2 regular, in the sense that if you take an L2 function, the solution of the problem is going to be an H2 function. So it goes from L2, where this little L that is reaching here is 0, to L2 plus 2, where here is the H2 semi-norm of the solution itself. Okay. So we assume that this is the case, and we study now what happens to the theorem when you have these three properties together. Okay, so when you have these three properties together, whenever you see the V norm, you can replace the V norm by the K norm, and whenever you have the H norm, you can replace the H norm by the S norm that you have over here. Okay, so let's try to understand what is happening here. Well, in this particular case, what you have is then what you have is the following: the infimum for VH in capital VH of phi G minus phi H, norm V, this is certainly smaller or equal than the phi G minus phi H norm V, sorry, phi G minus the interpolation of phi G itself, norm V. And now let me just replace the norm V with the norm K that I have here. Okay, so this is the norm K of omega. And now I can apply the result that we know from the theory, provided that you exploit the regularity that you have here on the right. So the idea is that with VH minus phi, I can say that this is controlled. I have to put minus K here. So this is H minus K, which is related to this guy. And now I need to understand what is the regularity of phi G, and the regularity of phi G is L plus R. So I have minus K plus L plus R, and this is semi-norm phi G, L plus R. And if I look at this guy over here at this point, provided that L plus R minus K is greater equal than 0, I can use this. Okay. So if this is the case, so if I have something which is greater than 0 in terms of L plus R minus K, then I can use this. And of course, this can be bound by, so if I just write the first part, VH of, sorry, let me bound VG minus IH of VG. So we have K omega. This is H L plus R minus K, semi-norm VG L plus R. And of course, this is bound by H L plus R minus K. And this is the semi-norm, the actual norm G L that we have here. And since this is the full norm, what behavior is the full norm, then provided that L is greater or equal than S, what we have is that phi g minus the interpolation of phi g can be bound by H L plus R minus K norm of G S. And here, the essential part is that I go from L to S. And since I'm going from L to S, when you take the infimum of that divided by the norm of GS, which is exactly the norm that I'm using for H, then what the conclusion is going to be is that the norm of U minus UH is going to be controlled by the error that you make in the space V, so norm of U minus UH in the space V, multiplied by H to the power L plus R minus K. Okay? Does that make sense? So, of course, now, if you know how to bound the error for V, this is going to be something that appears in the case of the L2 error, for example, will appear on the right-hand side with the constant of elliptic regularity, which tells you what is the regularity of the operator A, or the boosting regularity of the operator, actually of the transpose operator, so AT. And for us, we say that this is R. And if you use L2, then this L here is a number that is equal to the regularity of G. Sorry. If I'm using this, let me just use L equal S in this equality, not more equal, because otherwise I would have to put things there, and this is S plus R minus K. Sorry, otherwise things don't work. And I'll show you what happens in the other case. Okay, questions so far. So let's take a look at what happens in this particular case for Poisson. So, for example, A on omega smooth. In this particular case, R is equal to 2. So R is 2 regular. And what we have is that V is, so the norm V is exactly the H1 norm on omega, and the norm H, we take the L2 norm, which we call this zero norm. So for the Poisson case, what we have just proven is that if you take the U minus UH norm V, this is the result that we had above. This is more or equal than H to the power, so norm V at this point is 1 omega, is H to the power K, semi-norm U, K omega. And now what we have just shown is that the U minus UH L2 norm is controlled by U minus UH in the H1 norm, which we have just written, times a power H, which is to the power S plus R minus K, S plus R minus K, and all of this is equal to 1 in this particular case, because S is equal to 0, R is equal to 2, and K is equal to 1. Okay, so in other words, you obtain the following two estimates. You obtain U minus UH in the H1 error is H to the power K UK omega. This is 1 omega, and it's a global estimate because the space VH is included in H1. And the L2 error for UH, 0 omega, is controlled by H to the power K plus 1, the same error that we had above. And this is the optimal error estimates for finite element methods for the H1 and L2 and the L2 error. This thing, of course, is only possible if the operator A has an adjoint who is 2 regular. And this, of course, the regularity of the adjoint operator can be proven only for certain types of discretizations. In particular, it's simple to prove for regularizations which are, sorry, there's an issue here. This is not K. This that we have here is actually K plus 1. Sorry. Okay. So it's simple to prove the two regularity assumptions for the Poisson operator, and the fact that you have conforming discretization, so the H is included in V, makes life easy for the discrete part. In terms of non-conforming approximations, then this adjoint regularity is a little bit more complicated to prove, and the orthogonality is a little bit difficult for a very simple reason. And the very simple reason is that it may no longer be possible to actually plug in the operator the U minus UH if UH does not belong to the space capital V, because the operator A in that case is not controlled. You cannot apply the operator A directly to UH if you don't have this type of conformity. So if VH is not included in capital V. So that falls down and you have to work a little bit harder. So in that case, you're going to have also additional terms that will make the difference between a H applied to UH and A applied to U. So you have some additional terms that appear. I'm not going to discuss about this in particular because this is going to be part of Professor Andrea Cangiani's course in one of the next courses that he's going to do. Okay. So now, one of the things that I've done that is going to be very useful and that we are going to be using a lot for all the various analysis is the inverse estimates and trace estimates. So let's introduce this arguments right away. So inverse estimates. What are inverse estimates? So inverse estimates are estimates in which you try to control weaker Sobolev norms with higher Sobolev norms. So in general, it's trivial to say that norm of u k is controlled by the norm of u s whenever s is greater or equal than k. And that's for every u in h s of omega. Okay, so this is simple. And for Sobolev norms with integers and Sobolev norms also with fractional indices, we will see this later on. This is trivial simply because the norms that are written on the right are contain the norm that is written on the left plus additional terms, which are positive. So this inequality is very simple to write, also in the continuous case. The inverse inequality, and that comes from that gives the names. The inverse is possible on tau h for objects, actually not objects, sorry, for elements of the H. And let's start by looking at this and by proving this for simple cases. So the idea here is that we are going to show this for the following cases. So we will show the following things. Local estimate, local inverse estimates. We start with this, and then we generalize this to global ones. So let's assume that we have a FE, which is the collection, the usual collections that we have: T hat, function P hat, sigma hat. Okay, and let's say that we have L greater or equal than 0, such that P hat is in the space WL infinity of T hat. And so this is much more general with respect to just polynomials. So this applies to more complicated spaces as long as you have some L infinity control on the degrees of freedom. This is important. So you want to have boundedness of all the functions that are there and all the derivatives up to the order L for the finite dimensional space. You do not allow, for example, logarithmic functions or things like that in your finite dimensional space, but not necessarily polynomials. So this will be the first assumption that we have. So we have L0, that's property number 1. Now property number 2, we assume H is going to be smaller than 1, smaller or equal than 1 actually. And H is the size of all the various things. And we are assuming that this local finite element space generates a global finite element space, which is transformed through Tm equal Fm of T hat, and Pm is equal to the push forward through Fm of P hat, and the same is valid for sigma hat, push forward through Fm of sigma with respect to sigma hat. Okay, and this is a finite element, so this is the Fe equal Tm P hat m P m and sigma m. Okay, and we assume, for the sake of simplicity, that Fm is affine. whatever we say now is also valid whenever you don't have a fineness. Some details change. I'll tell you exactly what are the details that change, where they actually change. So given these three properties, what we want to show is that then the norm of B hat, sorry, the norm of V measured in the L, with the L degree of regularity that you have over here, P, T, M. This can be controlled with the power, which is K minus L norm of V K P T M. And this is valid for all K, which is smaller than L, and for P, which is between 1 and infinity. So what I'm saying here is that in the finite dimensional case, when you do local estimates, you can actually control higher order norms. So L is greater than K with lower order norms, provided that you pay with enough powers of the grid size. So in other words, if you think about this in terms of finite differences, this is telling you that if you look at the H1 norm of a finite dimensional space, the H1 norm of the finite dimensional space can be controlled by 1 over H times the L2 norm of the same function. Okay, and this is because you're defining things in a finite dimensional space. And the proof is quite simple, but it requires a little bit of working around. So let's do the proof, and then we'll go forward with some of the applications. So the proof of this starts with step 1. All finite dimensional norms are equivalent. So one could start by this and say, okay, then the inequality that is written up there is true. And of course, this is exactly what we want to show, but we want also to show that there is a constant in front that depends on H. So the equivalency on all the finite dimensional norms, which would be included in the constant that are hidden into the symbol, it's not enough for our purposes. So we want to actually prove that there is something that depends on the size of the grid, and that the size of the grids here, that it's also actually, this is since we're taking the local estimate, this is actually HM. And I'm assuming that the shape, the triangulation is quasi-regular. So if you don't want to make these assumptions here, you can have rho m to the power minus L here, and use rho m instead of HM to the power minus L. But of course, this is for quasi-regular, which I maybe didn't say here. I didn't say this here. And for every m, HM is greater. Okay. So there exists a sigma such that for every m rho m is greater than sigma HM. So we are assuming that this is the case, and we pay the price here. So first of all finite dimensional norms are equivalent. So we actually start by applying this to the actual finite element space P hat. So for every P in P hat, this is the finite dimensional space for the reference element. What we have is, if we take the P hat norm, let me call it V instead of P, otherwise it confuses with the P of the norm. So we have the BLP hat VLP T at is the same thing as writing V hat 0 P T hat. So no matter what you do, this proves that in the finite dimensional case, for the reference element, you have equalities of all the norms. Simply because all of them are finite dimensional and they are of course equivalent. Okay, and now we use the same trick that we had before, and we let V be V hat composed with the inverse of the affine transformations. And with this, we know already, we did this several times already, so let me just report this here. Then we can prove that VLPTN is controlled by HM power minus L, and there will be the Jacobian of the transformation on the element M, which is a constant number, the determinant of the Jacobian of the transformation, constant number times power 1 over P. And this is the B hat L hat. Sorry, this is not L hat, this is L P D hat norm. And now we exploit the fact that all of this are equivalent, and then we simply keep proceeding. And what we obtain here is that this is the same as writing HM to the power minus L, still JM 1 over P, and then we have B hat LP. Instead of L here, I put 0 P T hat, so this is 0. And I'm using 1 by this. And now I go back. So I apply the inverse scaling argument to this guy over here, and there's going to be no powers because there's a 0 here, so there's HM to the 0 power there, but this is going to cancel out the JM to the power minus 1P. So you will get at this point HM to the power minus L, and this is going to be the semi-norm V. And of course, if this is the 0 norm, this is going to be the full norm in the 0 case. And this is the full norm 0 P T hat. Okay. And now I'm in the case in which H is smaller than 1. And so what I'm asking here, since H is smaller than 1, then I can say that in the sum, the norm VLPTN is equal to the sum over the M, which are smaller or equal than L, of the semi-norm V. So we have this to the power P, we have this to the power P. And now if you take all the sums, since H is more or equal than 1, the only one that is going to be retained, the largest one, which is the one that is the biggest one, is the one with the highest negative power. Okay, so since this is the highest negative power, what we get here is that the norm V to the power P L P T M is controlled by H M to the power minus L to the full norm V. Sorry, there's no power P here on the left anymore. And this is going to be 0 P T hat. And simply because I'm applying this as the sum, so I'm insert here, insert 2 here, and exploit H smaller or equal than 1. And 2 is this. Okay? So this shows for 0, then everything works out. Okay. So what I'm telling it's if I take VL, so the L norm of V, where L is a positive number, then I can pay negative powers of H and estimate that with the L2 norm for every function V, which is a finite dimensional object composed with a finite transformation of the finite dimension. So V, and this belongs to B hat, to Bm. Okay, so for any V in Pm, you have this property. Okay. Okay. Now, of course, we have to show that this is valid also when you take different norms here on the left and on the right. But this is quite simple to do. So let me just split this into two particular cases. So let's assume, for example, that we take 0 smaller or equal than k, smaller or equal than L in this particular case, and let's take a 0 smaller or equal than alpha smaller or equal than L, where alpha is the multi-index. Okay. So now for any multi-index, if the norm of alpha is smaller than k, well, then one can say directly, one can show directly, it takes the L2 norm of the alpha derivative of V, and this, of course, for any V which is in finite dimensional space again, and you take the L2 norm of this guy, this is PTM, and one can show this is smaller or equal by the fact that you have this property, the fact that this is smaller or equal than L and that this is smaller or equal than K. Then if this is smaller or equal than K, you can actually bound this with the correct direction by saying that this is smaller or equal than the normal V L minus K. I'm just checking whether this is correct. Yes, I have this over here, and I have this. If this is smaller or equal than K, then I can do that because this L minus K is positive in this particular case. And if this is positive, then what we have here, I can now apply the inequality that I have just proven. So this is HM with the inverse sign K minus L of this guy over there, and then instead of writing this on any particular norms, you write this for the 0 norm. So this for the 0 P TM, and now you can keep going in this direction, and this is actually smaller or equal than HM K minus L, and here, since that's the full norm, you can write the full norm with the order K on the right. So you can get this smaller or equal K P TM simply because K is greater or equal than 0. Okay, so the passage is to figure out whether this is positive, this is true or not. And if this is not the case instead, so for example, if you have that L minus K is smaller or equal than alpha, smaller or equal than L. So in other words, you can no longer say that alpha is smaller than K in this particular case. Then if you write it in this way, you can always say that there exist beta and gamma such that alpha is equal to beta plus gamma, and such that the normal one of the two is equal to the lowest part, so it's equal to L minus K, and such that the other one is smaller than K. Okay, so if you have this, smaller equal than K. So if you have this, then you split basically the derivatives that you have above into two separate derivatives. So instead of writing the alpha directly and then estimating the alpha 0 PTM, what you do is you write that as the beta applied to the gamma, because you have that beta plus gamma is exactly equal to alpha, and then you measure this in PTM. And since you've already done the estimate above, then this is smaller or equal than the norm B gamma. And here you can actually write L minus K, because you have that beta is equal to L minus K. And once you have done that, this simply says that you have h to the power k minus L, and here you have d gamma v 0 by the estimate that we had above. So this is 0 p tm, and now of course you keep going and you keep having h to the power k minus L, and you can plug v power k p tm here on the right, simply because the gamma that you have here is strictly smaller or equal than k. Okay. And now the thing is, of course, if tau is quasi-uniform, if tau h is quasi-uniform, then for every v in capital VH, so this is valid for VH, you have to be careful. This is valid for, you can still write the same thing. So you can write V norm as I used K and L there, so let me just use K and L also here. H to the power K minus L and normal V K omega. And in this particular case, this estimate is global, provided that is global for, now I've chosen the wrong numbers, the wrong letters. Let me write, instead of K, let me write another name here. So this is going to be R and R. So this is 0 smaller or equal than L, and R smaller or equal than K plus 1. L is larger, so this should be R smaller or equal L smaller or equal than K plus 1. Okay, so this is valid for, I mean, if you increase K plus 1, so if you increase this to something which is over K plus 1, of course, it's no longer useful. And the reason why it's no longer useful is because if you take any K plus 1 semi-norm, actually, it's not useful up to anything greater than K, to be precise, because any K plus 1 semi-norm of the finite dimensional spaces is going to be equal to 0 everywhere. So this is not going to be useful anywhere. But it's global for 0, R, L, smaller than K, for every, when the H is included in H to the power K of omega. And of course, the reason why you want to have this is because we're writing global estimates of these guys over here. So you want to have that the largest object right here on the right is contained on the space. Make sure that the norms that you write over there are contained in the space. If you take HK plus 1 semi-norms of these guys, what you're going to get locally is that all the HK plus 1 norms of these objects are going to be 0 because of the of the fact that you're using polynomials of order f to k. Okay, so let's take a look at what happens for the next topic that I want to discuss. So this is essential to prove a lot of the results that we're going to be using in the next weeks and in the next days. So let's keep this in mind, and we'll go back to this in much more precise forms later on. And okay, let's move to trace spaces. So trace spaces and trace inequality. Okay, so the context here is the following. So we assume you have omega, which is a Lipschitz domain, with gamma, which is a Lipschitz curve. And the context that we are assuming here is that we would like to understand how to make sense of functions evaluated on the boundary of these guys. Okay, so function evaluated on the boundaries of these guys makes sense if u is C0 of the closure of omega, then u on gamma makes sense pointwise. What if u is in hk, which is not included in C0 of omega? For example, h1 of omega for d greater or equal than 2. Okay, so h1 of omega is not a space which is continuous in dimension bigger or equal than 2. Okay, so how do we make sense in this particular case? So the idea is we call this guy, so a function, let me just write gamma in this way for the moment, a object that goes from omega to something which is defined on gamma. Okay, so so I cannot write it in this way. So let me write it in a better manner. So let's assume that the functions that we're looking for are so we would like to understand when this expression makes sense for Sobolev space, for Sobolev norms. So for this particular discussion, I'm going to assume we're using Sobolev norms with index p equal to 2, so just hk norms. Of course, whatever I'm saying is also valid for WSP general spaces. So let's just use simpler definitions, because this is what we're going to be using for most of the examples. So Trace theorem says the following. So for S in the interval 1/2 1, omega Lipschitz, there exists a unique linear bounded mapping gamma that goes from HS of omega to HS minus 1/2 of gamma, such that the norm of gamma V in S minus 1/2 gamma is smaller or equal than a constant times the norm of V S omega. and such that for every u which is in C0 of omega bar, gamma of u is equal to u. Okay, on gamma, the restriction of the pointwise restriction. Okay. Question so far. So this is the first part of the theorem, trace theorem, part 1. Second part, gamma admits a bounded right inverse E, which is the extension of the trace, and E goes from HS minus 1/2 of gamma to values HS of omega, and it is such that gamma E of V is equal to V for every V in HS minus 1/2 of gamma. Questions so far? Okay, so now the main question that one should ask, so of course, the fact that there exists a bounded right inverse also implies that the operator E is a linear operator, and also implies that you can actually bound the norm S into the H1/2 into HS minus 1/2 norm. One way to define the HS minus 1/2 norms, so in this particular cases, we are looking for norms which are not integer norms. So in a certain sense, you have several options and several possibilities to define what it means for a space to be a fractional space where S is not an integer, but it's a real number. So for those spaces, there's 3 different possibilities. So how do we usually define those fractional spaces? Well, we have 3 options, actually several options. But let's start by looking at the most common ones that are used in the literature. So option number 1, omega coinciding with RD, then one uses Fourier transform. And let me define what a Fourier transform of a function V is. So the Fourier transform of a function is defined as 1/2 pi elevated to the power d/2 when you have d, which is the dimension, and this is the integral on RD of the exponential of minus I xc dot x v of x dx. And this object is written here on the left is evaluated at xi. And if you have this, then one of the nice things about the Fourier transforms in RD is that if you take derivatives with respect to the xc variable or with respect to the x variables, they appear as in the transformation of the Fourier things, just as multiplication with powers, positive powers of the exponents. So in other words, in this particular spaces, definition of the S norms can be written as for any real number S is usually defined as the L2 norm of 1 plus something square elevated to the power S/2 and you take b hat, which is the Fourier transform of this guy, 0 RD. So in other words, you define the norm through the norm of the Fourier transformation of this guy. Okay. The definition of the fractional spaces is given by the closure of the infinity with complex supports of RD. So HS of RD is the closure of the space C infinity with complex supports, closure with respect to the norm S RD, which we have just defined. So this is one option. So we define this for RD and we use RD. Of course, this is okay, because in RD, it makes sense to compute. So the rationale behind this is that if you take the derivative of these functions with respect to psi, for example, what happens is that you would get exponentials of you will get exponentials of x outside of your transformations. Okay, so if you actually take this, you will get the derivative with this respect psi is minus I x to the power s for s a positive number, for a positive real number. And if you take the inverse Fourier transform of something that contains the inverse Fourier transform contains actually the same thing, just defined by interchanging x and psi. And if you take the derivative with respect to psi in the other direction, you get exactly something that contains the powers of x. So you can take derivatives in one space and take the transformation with respect to Fourier, multiply by powers of psi and transform back, and you get exactly the definition of the anti-transformations of derivatives of arbitrary order in this particular case, because the derivatives can be seen when you transform in Fourier space with multiplications with the object in the other case, and this multiplication doesn't require s to be a integer number, but it's well defined for any s, which is a real number. So you define this in general in RD with an integer number, with any real number s. So in the particular case, instead of the of finite spaces, finite domains, like for example omega in RD, then one can show, and this is it's a difficult proof, it's not a trivial proof. If you have omega Lipschitz, the space HS, where S is given by an integer m plus lambda, so m is an integer in n0 and lambda is in the interval 0, 1, then you can define the S norm of this object as the M norm, as you would do in the standard case for the standard norms. This is generalized for all. It's also valid for all order cases, also for the non-real number case. So you define this through this usual norm. This is in n0, so this is okay. And then you add the semi-norm lambda, and the semi-norm lambda is defined in a way which is particularly interesting. So this lambda over here is defined as the following. So this is lambda omega is the sum for alpha is equal to m of the integral of the double integral omega, and then instead of taking the usual incremental difference, one takes the incremental difference integrated over the domain. So this is the alpha u of x, the alpha u of y, and this dx divided by uy is divided by x minus y, and this is I think it's power 2 here, and this is in the power 2. I don't remember if it's 2 minus plus 2 plus 2s, I think, in this particular case. Let me check. So the two which is in the front should be the dimension, and this should be the power of the space which is there, which is this 2 over here, and it should be the s which is over here. Yes, so this is the correct case. This is in dx. So this is a very difficult norm to treat. So it's not something that you would like to have in your day-to-day calculation. So there's alternative norms that you can use. And then one defines H0 of omega as the closure of C infinity with compact support in omega with respect to the norm S that we have defined there. And this norm S is actually the usual norm, the one you would have to use for these types of things. Okay, so why is this useful, and why do we need to take into account of the trace spaces when we take this? So why is it important to have in mind why the trace space is transformed in this way? Well, let me give you a explanation in an example that uses the inverse inequality plus trace inequality. So inverse plus trace inequalities. And let's understand what does it mean to apply the trace inequality to a finite dimensional space and to a finite dimensional function. So if you do that, what you obtain is the following. So it's let's assume that you have a function u, which is in the polynomial k, in the polynomial space of t, and let's assume that this is in the included in this space hs of k. Okay, and we need to have, for this to make sense, that s is greater or equal than 1/2. Okay, now what I would like to see is I would like to measure the norm of u on the boundary of the element t. So this is going to happen a lot of the time when you do the analysis, and in order for this to be possible, one should take a look at the s minus 1/2 norm if I want to apply the trace estimate that I had above. So this is going to be, I take the boundary of the element t, and I take the s minus 1/2 norm on the element of t, and by the theorem that we wrote above, this is controlled by the norm of u as t. And now this is with s which is greater or equal than, strictly greater than 1/2. And of course, what I would like to have is I would like to control, to have the same type of controls, the same type of norms that I have here on the left, on the right. And especially, this is especially true if you have, for finite dimensional spaces, you want to have the starting point and the ending point to be integers, because you know how to construct very easily integer norms, but you don't know how to construct easily fractional space norms. So one exploits the definitions of the inverse inequality that we had before, and obtains here at this point that you can actually bound this by the results that we just wrote before. This is like a power h. There's minus s to the, I mean, according to what I want to write here. So what I will write here is that this is going to be equal to some arbitrary number. I have to choose a letter, but it's not S, K, T, P, or R. So this is to be R, for example, or K. K is K. No, because I used it there. So let me say this is R. t. And now what I have here is this is r minus s, normal view, and this is for every u which is nu dk. And what you shows you is that you pay with a fractional h. So let's assume that r minus s is equal to 1/2 in this particular case. So you would have back the same type of norms that you have on the s minus 1/2 here. So let me show back this with a completed sample. So for example, we are going to see this type of inequality a lot of the time. So we have the gradient of u dot n, and we want to take this, for example, on 0 dk. And this is usually controlled by the full gradient of u on dt, sorry. This is again dt. And this is smaller than a constant gradient of u. Now at this point, I go 1/2 t on the full t instead of going on dt. And this is smaller equal than h to the power minus 1/2. Now the gradient of u 0 t. And now, of course, this is h to the power minus 1/2, 7 on u 1 t. So this gives you an idea on how to use these types of inequalities. So it allows you to control for finite element functions what's the norm of the gradient on the surface of the face with respect to the full norm on the boundary, the full norm on the actual element itself. So I won't have the time to use this for a priori error estimates, but I will do this before the practical lecture, if we do this in the practical lectures in terms of posterior error estimation. So I have to figure out whether I'm going too fast with the exercises, and if I'm going too fast with the exercises, I will stop and I will come back to this. So let me stop here. I'll stop sharing